Welcome to this part session. So I am Javier. I'm from the postdoc researcher at the Free University of Brussels, and I recently joined to the DISPAT project. So my colleagues will present you about the work they are doing in this research, but I will start with a very brief description of the project to put in context what they will be presenting. So this project that goes for digital twin for synchromodal transport is a applied research project funded by the Flemish government, and it's a collaboration of 3 Belgian universities, so the Free University of Brussels, the University of Hasselt and KU Leuven, and also BIL, that is the Flemish Institute for Logistics. But it also comes with the cooperation of several private companies, mainly logistic operators and retail companies. So the idea of this patch project is to develop a platform to provide a test bed for synchromodal transport by means of a digital twin environment. So the idea is to generate this digital twin environment, a simulation approach that is continually fetched by real data, but also can, on the other direction, give information to the real system in order to make better decisions to make this logistics system more efficient. And therefore, the idea is to strengthen this platform by using or by incorporating new algorithms related to inventory management, to network planning, and always considering the uncertainty in different levels. And it's also important to know that this digital twin aims to integrate decisions of both short and long haul transportation. So that's part of these contributions. So regarding those different aspects of the project is that the research work is divided between the partners. So the research is done by the 3 universities, where VUB, the Free University of Brussels, acts as the scientific coordinator, and is in charge of developing the core of this digital twin environment and to integrate the different algorithms or approaches that are developed. Then KU Leuven takes a supply chain perspective, looking at the smart replenishment algorithm. That's it from the point of view of the shipper to decide according to their current algorithms how much should they order and using what mode. And finally, Hasselt aims to take a look from the logistic operator perspective. So the problems studied there are more related to routing problems and capacity allocation. And finally, the Flemish Logistic Institute is the cluster facilitator in charge of valorization and dissemination. So now I will let you with my colleagues. So to start with, from VUB, Shiji Wang. She's a PhD researcher at VUMOVI, and now we will listen to the work she's doing.
Hello everyone, my name is Zhiyi Wang. I'm a PhD researcher at VUMOVI. On behalf of Dr. Claude Moments and Professor Cathy McCallis, it is my honor to be here presenting in this special session of Dispatch project. The project combines forces with 3 universities, VUB, KU Leuven, and Hasselt, to conduct a synchromodal study within the themes of digitization and sustainability. I'm here today to present to you about a literature review with 5 classification, which is firstly proposed for sustainable logistics. And with this classification, we're going to explore the question that is synchromodal transport leading to more sustainable freight transport? Therefore, I've divided my presentation into 5 parts, which will take around 20 minutes. Firstly, I'll look at the introduction part, and then the methodology for the whole literature review. Thirdly, but most importantly, it's the 5A's classifications for synchromodal transport. Then will be the results, discussions, and the conclusion. So for the introduction, as we all know that sustainability is always the core concept of Europe. Transport accounts for a quarter of Union's greenhouse gas emissions, and this continued to grow. The Green Deal seeks a 90% reduction in these emissions by 2050. And you could also say in the charts, as a matter of fact, not only road transport, but also the road-free transportation accounts for a large proportion of global green gas emissions, especially for carbon dioxide emissions. Therefore, to mitigate the negative environmental impact caused by free transportation, intermodal free transport can be a solution with a modal shift strategy, applying multiple transportation modes such as the railway, road, and inland waterways. Nevertheless, according to the recent research, part of the carriers who still prefer road transportation for shipment, and they believe that the intermodal transportation is relatively slow and inflexible with limited service providing. Therefore, the integration with new technologies and proposed new concepts have the ability for a flexible and dynamic improvement to make intermodal transport more widely accepted. And that's why we're talking about synchromodal transportation here, which can be perceived as real-time dynamic intermodal transport with higher flexibility, feasibility, and more selectivity, since modal shift and rerouting are all relying on the real-time circumstances. And also it aims to support the service providers to make more appropriate decisions. So with synchromodal transport, it will be beneficial to meet the demands from different stakeholders, provide a strategy of decision-making, and improve sustainability. And at the beginning of this literature review, we actually gave the attention to several other literature reviews focusing on synchromodal transport. And after reviewing those typical papers, we found out that there are basically no reviewing papers focusing on the results of implementing synchromodal transport and examining whether synchromodal transport can eventually facilitate sustainability objectives. So that's the reason why we have this or conduct this review. Actually, this review utilized a classification named 5As of sustainable logistics to provide a critical perspectives for sustainability in synchromodal transport. And in order to explore the answer, we have several following research questions to support it. Firstly, it's about the classification of the current research on synchromodal transport according to the 5As of sustainable logistics. And secondly, is to which of the 5As do the results of reviewed papers on synchromodal transport meet? And then is what are the key elements for the realization of sustainability in synchromodal transportation? So, secondly, for the methodology of this review, first of all, we formulate the research scope, which is described for the introduction and also to discover the research gap. And secondly, the papers are selected to form the database of this review. And thirdly, to use the 5A for the paper's classifications. And with the step 4, we mainly focused on the results of those papers and find the linkage between different studies. And the last step is to identify the license and also to discuss about the future prospects. So for the 5A classifications, which is a classifications of innovative concepts for sustainable city logistics in the beginning, and this new classification of sustainability in the logistics proposed by Professor Katy McCallis and Brankin in 2017, taking into account different challenges in sustainable logistics. And it is firstly structured following with 4 A's, which are awareness, avoidance, action shifting, and anticipation. Additionally, the researchers recognize the presence and importance of the different stakeholders within logistics. Therefore, the 5th A, called actor involvement, is proposed, and which will also be considered in this review. So we have the 4th A classifications in this review representing awareness, avoidance, action shifting, anticipation, and also the actor involvement. So more specifically, awareness is about letting different stakeholders become aware of their influences by their actions, including different methods for measuring those influences and establishing various programs and certificates. And the avoidance aims to prevent unnecessary transport and vehicle kilometers by better collaboration and bundling, avoiding packaging waste, improving load capacity and scheduling optimization, etc. And for accident shifting, it is beneficial to shape the goods by switching more environmentally friendly modes or considering the non-peak hour delivery. And anticipation is about the utilization of new technologies, which is not only by applying the novel types of carriers, for example, the autonomous vehicles, but also by developing innovative information and communications technologies. And it is really important actually for the synchromodal transport to coordinate and synchronize with multiple stakeholders, since they always have interactions and influences with each other, and actor involvement is necessary to be considered. So the focal point of this review is the research results of different papers in the 5A's classifications, and then we will show you the discussions and some results about it. So to answer the research questions, firstly, for the classifications of current research on synchromodal transport according to 5A's, we actually found out that there are several studies have the combined research objectives, or they could be classified in different A's or more at the same time. For instance, it is more often to capture the combination of avoidance and accident shifting, since improving capacity utilization and the rate of modal shift are the main measures for synchromodal transport. Therefore, we discovered this relationship between 5A's, which is shown in this slide, in this picture, mainly from two perspectives, the operational one and also the strategic one. It is always like the categories about avoidance, accident shifting, and anticipations always provide researchers from the operational perspectives. They tend to take various actions by using quantitative methods with model development, simulations, or optimization methods. And on the other hand, awareness and actor involvement have a larger scale covering both operational and strategic perspectives, especially for the actor involvement. They are not only related to the development or design of the methods or models for facilitating the cooperation of different stakeholders, but from the different individual perspectives by holding the surveys or interviews with different size or types of companies. Then they could have the perspective from shapers, logistics service providers, operators, etc. All of these diverse aspects are aimed to deepen the collaboration, information exchange, and increasing the application of synchromodal transport. So the relationship between each circle of the 5A's can be regarded that they actually interacted with each other and they are not isolated from each other. And further exploration can be conducted to check what kinds of impacts or interactions they have on each other and the relationship between these effects with the sustainability in synchromodal transport. Also, here is the distribution of different A's in diverse years, showing in this chart. The yellow dots present various reviewed and classified articles, and it is clear to discover that from 2016 to 2019 has a higher amount, and most of the studies focusing on the operational level. The studies of actor involvement are balanced distributed in different years, we could find that, and which can be reflected that due to the continuity of stakeholder research, it could be a little bit complex and difficulty of this kind of research, which needs more time and studies to find out the solutions or methods to improve the stakeholder engagement in synchromodal transport. And for the second research questions, to examine the results of each research to check if they're finally fulfilling the objectives that like what we expected for synchromodal transport can achieve for the sustainability facilitation. The results of different classifications are actually different, especially between the operational and the strategic perspectives. As we could say in this chart, For the studies of awareness, avoidance, and shifting and anticipation, there belongs to the operational perspectives. There are almost 80% of the article results correlated to the sustainability. And for the left 20%, and some of them are focusing on the theoretical basis of the concept itself or the factors of the implementation, and others might just pay attention to the efficiency to reduce the transport time. But however, we could say pretty clear about the actor involvement. There are only 30% of it correlated with the sustainability or discuss sustainability. Nevertheless, the results are understandable actually, because most of these kind of papers are using qualitative methods, which are not like numerical results that can directly show the emissions reduction. Moreover, since there are wide aspects to be considered in stakeholder engagement, like there could be different types of actors, evaluation of critical success factors, platform establishment for stakeholders, corporations, etc. Most of the research need a series of further studies to support them. But totally, there are 70% of articles meeting the objectives related to the sustainability facilitation. And subsequently, to answer the research questions that what are the key elements for the realization of sustainability in synchromodal transportation, there are different charts corresponding to each classification are presented. We actually summarize 6 elements or 6 candidates after reviewing, which are man shift, real-time data availability, mode-free booking, coordination between stakeholders, information and data sharing, and authorizing. So here we could see in the act and shifting, the real-time takes a really large proportion of it. And also like a model-free booking, coordination between stakeholders, and information sharing are also being mentioned as well. And for the avoidance, the real-time and data availability, information sharing are the most frequent being mentioned in those kind of papers. And of course, for both of them, the real-time and model-free booking are mentioned. And for the anticipation, there are only 2 be mentioned, which are the real-time and also the information sharing and data authorizing. So from the operational perspectives of for the 4 categories we showed, it is clear to see that real-time takes a really large proportion in all of these 4 categories. And also the mode-free booking always occurred with act and shifting, since transportation operators have the flexibility to choose the modes of shipment, which is able to ensure the flexibility and accuracy of the mode switching. And moreover, the information sharing and data authorizing and also the coordination between stakeholders are significant elements for these categories. And for the awareness and actor involvement are quite obvious that both of them are in line with their own characteristics. And to improve the awareness, it is necessary to foster the mind shift with data sharing mechanism and collaboration of stakeholders. And to facilitate the actor involvement, the coordination between each other and the information exchanging are the key aspects. And due to these 2 classifications are tending to have more qualitative analysis, real-time data and data availability are really be mentioned. And in general, from an operational perspective, real-time information sharing and data authorizing and also the mode-free booking are the top 3 key elements to facilitate sustainability in synchromodal transport. And from a strategic perspective, man shift, information sharing, and data authorizing, and also the coordination between stakeholders are equally important to it. So, in conclusion, with the classification of 5 A's, we investigate and provide a critical perspective for sustainability in synchromodal transport. And the 5 A's actually represent awareness, avoidance, act and shift, anticipation of new technologies, and also the actor involvement. And after classifying and reviewing different studies, and firstly, we summarize the relationship between different A's in synchromodal transport, and all of them could have this kind of interactions with each other. And further research can be considered to check what kinds of impacts or interactions they have on each other, whether the influences are positive or negative or etc. And what is more, it is also useful to check the relationship between these effects with the sustainability in synchromodal transportation. And next, for checking the results of multiple researches on synchromodal transport, we found out that almost 70% of studies achieves objectives like we expected synchromodal transport can achieve for sustainability facilitation. And meanwhile, we summarize the key elements for the realization of sustainability in synchromodal transportation. The real-time information sharing and data authorizing and modal free booking are the top three key elements from the operational perspectives. And also the man-shaped information sharing and coordination between stakeholders are quite important from a strategic perspectives. And what is more, for the future research dealing with uncertainties and disturbances in the dynamic synchromodal network is an essential aspect to focus on with the study going deeper. And it is always worth checking the main research questions about whether the synchromodal transport can lead to more sustainability when we have more projects making further progress or have more studies get their results. So that's my presentation. Thank you very much for your attention. And if you have any questions, I'll be pleased to answer them.
Okay, thank you, Shiji. Can't turn my camera on. But okay, so yeah, we have a question from the public. So if you have any more questions, please make them in the chat. So the question is how these 5 A's classifications reflect the 3 main pillars of sustainability.
It's actually these 5 A's could reflect the 3 main pillars of sustainability. For example, like the awareness, it could actually using different measures to evaluate the impact brought by the different stakeholders, like the carbon dioxide emissions costs and also the other costs related to the logistics. And so it could be highly related to the environment impact, and also for the avoidance, action shifting, and also anticipation, because they're using the anticipation, they're using the new technologies, and also the action shift and avoidance, they're aiming to provide better logistics service and by using the synchromodal transport. So after all of these actions they're done, there are always related to the economic issues, like if they are going to reduce the costs from the logistics perspectives. And also, like, for example, for the awareness, actually they're using like different decision support analysts to support it and provide more better managed of the operations. And also they could have the overall look at the whole business to facilitate the mind shift and also increasing the awareness in the further development of the synchromodal transport. And also for the actor involvement, actually it includes like different parties or the stakeholders inside of it, like the logistics service providers and also the transport planners and also their customers. And they could like present a guiding wheel for the future, like with different kind of like game designing or the participation to involve the different stakeholders, and to say and to if they could help them to form the mind shift and to reduce the cost and improve the service and also engage the collaborations. So I think the 5 A's could actually reflect this kind of 3 main pillars, but it could be from the different perspectives to see the problem.
Okay, thank you. So I think there are no more questions from the public. On my side, so you give a very nice description on the studies. How did they consider or how they analyze this sustainability? So, but my question went more on what about the conclusions of those studies? And so the main conclusion, you mentioned it also as a future work, so with more results. But until what you have now, is there a strong conclusion or strong evidence that synchromodality can be beneficial from the environmental aspect?
Yes, actually, these results are based on the papers I searched, but all of these kind of papers could they could be like in the start of the whole series of some researchers, or they just have not the 100% sure for the whole project results or something like this. So I think there could be more further research to do, and also related to these research questions we talk about here. And always focusing on the results, maybe we have more results carried out, and with more projects have their progress to show and to have their outcomes. And then we could see at that time to see back of this kind of problems or the questions, and that could be have the different results or related to it. But for now, the results is just based on the current papers we found.
Okay, thank you.
Yeah.
So then there is a comment. Yeah, so thanks for that remark. So if there are no more questions, I guess we can go with the next presentation. That's from so Professor Robert Boat and Hannah Jig, who is a PhD researcher. So let's see that.
Thank you for watching to our presentation. I am Robert Boete from the University KU Leuven, and together with my colleague Hannah, we will present the work that we are doing in the Dispatch project. As you may have heard from my colleagues, the Dispatch project is all about synchromodal planning. Synchromodality is one of the cornerstones of the physical internet. It's an innovative way to ship freight by making use of multiple transport modes, but in contrast to static intermodal transport, synchromodal transport makes use of real-time information about the network, about the orders that are coming in, and by making use of that real-time information, we can exploit that real-time information to replan the transport mode or the modalities at all times. That way we can use the modalities more efficiently, we can exploit the advantages of different modalities, and especially we can be more flexible towards things that may change over time. And that way, by integrating different transport modes, we get to an interconnected network of the physical internet. Now, what is our work of KU Leuven in the Dispatch project? Well, what we do is we develop decision support models to support a shipper that is thinking about how can I include real-time information in synchromodal transport planning. And then the second question comes like, what is now the value of using that information, that real-time information in synchromodal decision making? So without further ado, I'm going to give the floor to my PhD student, Hannah, who will tell you more about the work that we have been doing so far.
Hi everyone, I am Hannah, the PhD student of KU Leuven in Dispatch, and I will now talk about the research that we have done so far, where we look into synchromodality when we are dealing with stochastic travel times in the network. Why is it relevant to look at stochastic travel times? Because it reflects the unreliability that we see in the transport system. Things such as delays, congestion, disturbances, they all make that we do not have certainty in the travel times, but that we rather have an uncertainty, a stochasticity in those travel times. So with the characteristics of synchromodality, where we can adapt decisions to real-time information, it will allow us to make decisions based on the real-time information on the duration of the travel time. So we can adapt our transport mode decision to the duration of the travel time. For instance, when we are traveling a route and we see that the first part has gone rather fast and the travel time has been short, we might want to switch to a slower transport mode to benefit from potential cost or emission advantages. And on the other hand, when the part would have been slower, we might want to switch to a faster transport mode to make up for that delay so that we can still arrive on time. So with making those synchromodal decisions based on the real-time information, we can cope efficiently with that uncertainty, that stochasticity in our travel times. So what we did is we wanted to develop a decision support model to make decisions based on the duration of that travel time. On one hand, to see how can we adapt our decisions to that information, but also to gain some insight in what the value actually is of doing so, of making those decisions based on real-time information. All right, so that is what we did. We developed a decision support model that helps us in choosing the transport mode decision when we are dealing with those stochastic travel times. So we make our transport mode decision based on real-time information. And which information do we take into account? Well, firstly, we are going to look at the duration of the travel times, because these travel times are stochastic, so we can only know in real time what their outcome is. We will take that information into account. Aside to that, we also look at the schedules of our intermodal transport services to make sure that we can only select a service at the time that it is departing. And at last, we look at the available capacity on the services. So we can only select a service that has enough capacity available to ship all the freight units in our shipment. In this model, we take the perspective of an individual shipper who is forwarding his own single freight shipment, who is plugging into a synchromodal platform that connects him to the available transport services in the network. I will now start by giving a short example to clarify how the model really works. So let's consider a shipment that is forwarded from Rotterdam to Milan along a route with one intermediate terminal. What our model will do is it will support the transport mode decision at the start of the route and also in the intermediate terminal. All right, so we start in Rotterdam and suppose that it is optimal with our model to start with rail transport. When we travel this service, everything can just go well so that we arrive timely in the intermediate terminal. At that point, we might find it optimal to just continue our route by rail transport until we arrive at our destination in Milan. However, when we start in Rotterdam by rail transport, it can also happen that a disturbance occurs along the way so that we arrive at a delayed time in that intermediate terminal. At that point, it might be optimal to switch to a faster transport mode like road transport to make up for that delay so that we can still arrive timely in Milan. So as you can see, what our model did is it supported the transport mode decision at the start of our route, but also at the intermediate terminal. And it did so based on real-time information. As the example showed, in the intermediate terminal, we were going to look at real-time information on how long was the travel time for the first part of the route, and then we adapted our decision to it. So that is what our model does. Let's now go a little bit more into the formulation of the model. Let's start by looking at the input that we need for the model. Firstly, we need input on our multimodal transport network. So we need to know the terminals that are in place along our transport route between the origin and destination, but also the transport mode services that are present between those terminals. And we also need to know the schedule of those services, so we need to know at which times they depart. As we are dealing with stochastic travel times, we also need input on that, and we formulate that through a set of possible travel time durations, a set of travel time scenarios. And we also need a corresponding probability distribution on that. So that is how we model the stochasticity, which we need to input into our model. We also need our cost parameters. We need to know what the cost is of taking a transport service, of transshipping the shipment between different transport modes in a terminal. And we also are going to give the penalty cost for when we have a late delivery. At last, we have some shipment-specific inputs, like the number of freight units in the shipment and the delivery time of that shipment. And that brings us to the exact formulation of the model. Now, in this presentation, I will not go into any mathematics. For those of you who are interested in that, I kindly refer you to our published paper on this research where that is all explained elaborately. So what we do is we formulate our model as a Markov decision process. This is a framework that works really well when we are dealing with uncertainty in our environment. And why? Because a Markov decision process, it it takes into account that that stochasticity is present. It considers in the current decisions that we are making right now that in the future there will also be stochasticity, and that in the future we will also adapt our decisions to that stochasticity. And as it can deal really well with uncertainty, that's good for us because we are looking at uncertainty in the travel times. The outcome of the Markov decision process will prescribe an optimal action given the state of the system. For us, the action means the transport mode decision, either at the start of our route or at an intermediate terminal. And the state at the decision moment is defined by 3 elements. First, we are going to look at which services are available given their departure time. We're going to look at the capacity that is available on those services, and we will look at the realized travel time duration of the previous services, because it is this travel time duration that determines the timing at which we arrive at the intermediate terminal, which essentially is the timing at which we will have to make a transport mode decision. Now, these elements of the state, they actually define the real-time situation. They define the real-time information that we will take into account at the moment that we are making a decision. So by using this Markov decision process where we can take our action or transport mode decision based on that state, we can adapt our transport mode decisions to real-time situation. Of course, what is optimal? It depends on the objective, and what we will do is we will minimize the sum of transport cost and a late delivery penalty cost. These penalty costs are included because typically the slower transport modes are less expensive, so to make sure that we are still going to take into account the delivery requirements, we are going to include that penalty cost. Alright, so with that model we performed a numerical experiment to gain insight in the performance of synchromodal planning, and I'll now briefly walk you through the most interesting results. So what we first do is we compare synchromodality with an intermodal solution. Intermodality, it also combines different transport modes along the transport solution, but the biggest difference is that this transport plan is predefined in advance. So decisions cannot be adjusted to the duration of the travel time, which means that no real-time information is taken into account. So comparing synchromodality and intermodality, it gives insight in what the value actually is of using that real-time information when we make our decisions. So what we do is we compare synchromodality and intermodality with the cost of unimodal road transport. Why unimodal road transport? Because shipping solely by road is often done in practice. And what we see is that synchromodality outperforms intermodality with a 1.35% cost improvement. Aside to that, we wanted to see what the effect was, what the impact was of delivery time, service frequency, and shipment size on the performance of our synchromodal solution. So let's first look at the delivery time. Again, on this graph, we show the percentage cost reduction compared to when we would ship solely by road transport. And what we find is that when the delivery date gets longer, or equivalently when our shipment is less urgent, that the performance of synchromodality goes up, because you can see the cost reductions increase as the delivery time is further away. This is explained by the fact that when we give more time to ship our shipment, that we can substitute the faster modes for slower modes, which are less expensive, resulting in larger cost reductions. Interesting about this is that if we would go to a situation where we could plan better in advance and have less urgent shipments, that our synchromodal solution will perform better. Let's now look at the impact of the service frequency. We are going to look at the frequency of the rail and waterway transport services. And what you can see is that when these services get more frequent, that the performance of the synchromodal solution increases. So synchromodality will lead to larger cost reductions when services are more frequent, and this effect is strongest when we look simultaneously at rail and waterway transport services, as in the right panel. Now, this is particularly interesting because this means that if we can move more towards a physical internet where a lot of different logistic networks are interconnected and that we have more transport services available in that network, that synchromodality will perform better. And at last, let's look at the impact of the shipment size. We see that for smaller shipment sizes, synchromodality will perform better. Now we did our analysis for the number of freight units in a shipment and see that for smaller shipment sizes, the performance will be better. But this insight actually extends to smaller freight units as well. And that is interesting in a physical internet vision because it actually is in line with the physical internet idea to move towards these smaller modular shipping units like the physical internet containers. All right, so let's now look at what the prerequisites are if you would want to implement such a model in practice. First, of course, we need input on on those travel time scenarios and a corresponding probability distribution. This could be derived from historical data sets or from a simulation of the transport system. Aside to that, we need technologies that can track our trucks, trains, and vessels in transit to provide us with real-time information on that travel time duration. And at last, our model plugs into a digital platform that combines real-time information with the decision support model, so it feeds the information into the decision support model, but it also connects our shippers to transport services available in the network. All right, so to summarize what we did in our research is we developed a decision support model for synchromodal decisions that adapt our transport mode decisions to real-time information about the travel time duration, and with that model, we look into what the value is of making decisions based on real-time information, but we also investigate how the performance of synchromodality changes when different aspects of the input change, and we see that synchromodality does better when the delivery dates are longer, but most importantly, we see that synchromodality performs better when services are more frequent and when shipment sizes are smaller. And this is interesting because it means that when we can evolve more towards a physical internet, that synchromodality will perform better. All right, this brings me to the end of our presentation. This was a KU Leuven part of Dispatch. On the slide, you can still see our contact information, and there is also a QR code which takes you to my LinkedIn page in case you would like to connect. Thank you for your attention, and we are happy to answer any further questions at the end of the presentation.
Okay, thank you, Hannah. So we have a question in the chat. How do you combine scheduled service with non-scheduled services?
Yes, hi. Thank you, Jan, for your question. I hope you can hear me well. So your question on how do we combine scheduled services with non-scheduled services. So how we do it actually is something that is in terms of modeling. So at each time we are going to see for the scheduled services if they are available. So we really schedule the times in our model at which they depart, and then we see can we use them or not. For the non-scheduled services, which is road in our case, we actually just assume that it is available at all times, so that we can just order it at all times. But if we would want to introduce some kind of schedule in that, we could do that similarly to how we did it for rail or waterway transport services by including the times at which we can take those services which reflect those service departures times. I hope that answers your first question. I see that you also have a next question on how to adapt the model to a network situation where small transport unit will pass through a number of intermediate nodes. Well, the model actually is built for a particular kind of freight unit, and we can actually choose how large or how small that unit is. So it doesn't really matter for the model that or what our input actually is. It's just that we use one kind of freight unit as the input unit. So it just what it will have an impact on is it will impact the available capacity, of course, because then we have to transform that as well into that transport unit term. So it's not really a thing of changing the network per se. It's really of changing like the input in correspondence to that size of the freight unit. So I hope that also answers your question. I hope that was clear. I don't know if there are any further questions.
Okay. So no more questions in the chat. I have one question. So you are considering probability distribution for the travel times. My question is, are these probability distributions stationary or can they change along the time?
Yeah, so currently in the model, they are just stationary because they are like aggregated from, they are made from an aggregation from the transport system. But however, suppose that the probability distributions would change to a disruption that will last for a longer time, or that, due to, I don't know, roadworks or whatever, they might change, then we can actually just change those in the model. And this might even be done when we are already traveling with our shipment, and then we just have to change our origin to that intermediate place, and we can do it while being on the route because our model, it actually solves within just a few seconds. So if something would change in those probability distributions, we can really just do it while we are on our traveling route, because it can actually be solved in what is near to real time in just a very short time frame to get that new solution in correspondence to a changed probability distribution, if that would be the case. So indeed they are static, but there are possibilities with our current model to make it more dynamic if those probability distributions would change over time.
Okay, thank you. And then the last questions from my side. So you compare your results like with synchromodality with intermodality results. So that's decisions without real-time information and find these cost reductions. Isn't that like straightforward, or because then you are allowing just a more flexible results?
Yeah, so indeed, with synchromodality, we have this extra flexibility that we can adapt based on real-time information and really adjust to make the optimal decisions. And since we are minimizing cost, it only makes sense in some way that we are having cost reductions. But what is particularly interesting about this is that with our model and with that comparison to intermodality, we can really see what the exact value is. So this can be very useful to identify situations or corridors where we can see synchromodality will really be useful here, because now with our model, we can really capture that exact value of making those decisions based on real-time information. So that's where our model will be of value. Yeah.
Okay, thank you. So if there are no more questions, I think, so we can go for the next speaker, the next presentation. That's from Thibaut, that is a PhD student at U Hasselt. So the video, there it is.
Good morning, everyone. I'm Thibaut Delbar. I'm a second-year PhD student at the Logistics Research Group of Hasselt University, and I will be presenting a capacity decision support model for synchromodal transport under consideration. This research is part of the Dispatch project, which stands for Digital Twin for Synchromodal Transport. It is a project done in cooperation with our partners from the MOBI Research Center at the VUB, also with the KU Leuven and with VIL, which is the Flemish Institute for Logistics. But the objective of the Dispatch project is to facilitate synchromodal transport in Flanders, and this will be done with a digital twin platform, which I will briefly explain later on. Within the Dispatch project, our own focus at Hasselt University is on supporting logistics service providers with their transition towards synchromodal transport. This is because the combination of road transport with other transport modes is potentially cheaper and also more sustainable than unimodal road transport. But there are several ways in which synchromodal transport can increase efficiency. So, for instance, by increasing freight consolidation, which can also lead to higher vehicle fill rates, and by using more environmentally friendly transport modes. But these more environmentally friendly modes, such as trains or barges, can also be cheaper for long-haul transport. We're going to support logistics service providers with capacity planning under uncertainty. So this is because with unimodal road transport, trucks can be booked even in the short term. So for instance, if you receive an order today, you could still book a truck to deliver it tomorrow. and that's not the case with trains or barges. So with those transport modes, the capacity needs to be booked in advance. And besides that, trucks are also more flexible, so if there's suddenly an accident on the road, a truck can easily take a different road, whereas trains are stuck. So naturally, when switching from a more flexible transport mode, in this case trucks, to less flexible transport modes, need to account for this additional uncertainty. So we're also only going to consider container transport, and our scope is limited to a single corridor in the European network. Now I will give a bit more information on the digital twin. So let's assume that this is a timeline and it is currently time t. So up until now, we have collected real-time information on the physical system, and this information is constantly sent to the virtual system, also called the digital twin. So this means that we now have an up-to-date virtual environment in which we can perform various simulations and see what the effect will be of new incoming information, or what the effect will be of our own decisions. So based on this, we can generate different scenarios based on our own decisions and changes in the system itself. Ultimately, what we are interested in is what the best decisions are given the available information. So to obtain this, we would need to integrate optimization algorithms within this digital twin. And this is actually something that I will be working on, and from the point of view of logistics service provider. Now I will explain the transport planning problem that we would like to address. So consider the following network, which consists of several nodes and arcs that connect those nodes. Logistics service providers receive orders that must be shipped from their origin to their destination through this network. So for example, let's assume that an order arrives to ship 10 containers from point A to point B. The logistics service provider then needs to decide how those containers will be shipped. So it needs to decide which transport services will be used and how much capacity is required on those services. In this example, the logistics service provider might decide to ship 6 containers with services on the upper arcs and 4 containers on the lower arcs. Of course, the capacity decisions we just made were done after the order arrived. And in real life, this might be possible if only trucks are used, but other transport modes are usually booked before all orders are known. So now let's assume that those 10 containers were not an actual order, but the estimated demand, and the capacity has been booked in advance. So this means that the capacity decisions are actually made at the tactical planning level. So when the actual orders arrive, they can actually deviate from what we just estimated. So if that happens, the transport plan must also be updated. So let's assume that the actual demand is 11 containers from point A to point B instead of 10. This means that additional capacity is needed. So a possible solution is to book additional capacity on the upper arcs, which would lead to the following network. This would then become the new solution. So these capacity adjustments are done in the short term and are operational planning decisions. The actual routing of individual containers is also done at the operational level, which is different from tactical planning level, where actually only the total number of containers on each arc are considered. So those two decisions are part of the operational planning level. And because this update we just performed is done in the short term, it may actually not be possible anymore. So the total capacity per service is limited, and by waiting until the short term, it might be too late if all the capacity is already booked by other companies. So if that happens, capacity must be booked on services which are still available our own trucks. So in this example, this could become the new solution if there isn't enough capacity available anymore on the upper arcs. So this would then become our final network. As we just saw, logistics service providers are faced with several types of uncertainty. So the first type of uncertainty we've just seen is stochastic demand, which is also normal because capacity is booked in advance before all demand is known. The second type of uncertainty are stochastic travel times. Next, the remaining capacity that can still be booked later on is also uncertain because other companies might book it. So this is also one of the reasons why it can be preferable to book capacity before knowing all of the demand. Next source of uncertainty are deviations between actual capacity and booked capacity. For example, when a train arrives, the actual number of slots can differ from the number of booked slots, or wagons are set up for the wrong type of container. According to one of the logistics service providers that we consulted, this is quite common. Last type of uncertainty are sudden disruptions, but this can be relatively minor problems such as vehicle breakdowns or small accidents. But they can also cause major problems such as a closed rail connection. We also consulted two logistics service providers to learn which challenges they face with regards to synchromodal transport. So the first challenge they mentioned was how much capacity should be booked in advance. And this is mainly regarding train and barge capacity because slots on those modes of transport are booked before complete demand information is available. The next challenge is how many trucks to keep. But that's because trucks are still the go-to mode of transport in case of disruptions or last-minute order arrivals. Finally, logistics service providers would also like to know how to deal with disruptions in real time. We also performed a literature review to find out if similar problems were already studied. And from this review, we learned that the transport planning performed by logistics service providers is addressed in service network design problems. So out of all the studies on service network design, the ones with two-stage models are the most accurate. So in those two-stage models, what happens is that capacity decisions are made in the first stage before demand is known. And then the second stage occurs with complete demand information, and recourse actions are performed during that second stage. According to the logistics service providers we consulted, capacity decisions for trains are made about 6 months in advance. So this would correspond to the first stage in existing models on service network design. At this point, slots are still the least expensive. There's also a high number of available slots, but the uncertainty regarding demand is high. Complete demand information is available about 1 week in advance. So at that point, slots are the most expensive. There's also only a low number of slots still available, but there is very little uncertainty, since most of the demand is known, if not all of it. However, in real life, it's usually too late to cancel previous bookings at this point. So these two times would correspond to the 2 stages in existing models on service network design. However, in real life, decisions are made continuously whenever new information arrives. So it's not that realistic to wait until all orders are known before making changes. So we propose a different approach with this third intermediate stage would serve to more accurately represent real-life decision-making. It would happen at about 1 month in advance. So at this point, slots are slightly more expensive than 6 months in advance, but not as expensive as on a short term. There's also an intermediate number of available slots at that point. So whereas in the short term, it's quite possible that there simply aren't enough available slots anymore. This is less likely 1 month in advance. Part of the demand is already known at that point, so the uncertainty is lower compared to 6 months in advance. It is also still possible to cancel previously booked slots, which is something that cannot be done 1 week in advance, since it's too late at that point. So we then created a model with those 3 stages to support capacity decisions for logistics service providers. I'm now going to discuss this model. The first stage happens about 6 months in advance. At this point, the objective function is to minimize the total costs, which are made out of 3 parts. First, the cost of capacity booked in the first stage, then the expected cost of additional capacity that can still be booked in the second and third stages, and finally, the penalty costs for late deliveries. So the decision variables at this point are the number of booked slots per service and also per arc. We only have 1 constraint in the long term. That's a constraint which states that the total number of booked slots must be at most equal to the total number of available slots per service. The second stage happens about 1 month in advance and is quite similar to the first stage. So at this point, the decision variables are the number of additional slots booked per service per arc and the number of cancelled slots per service. There are also 2 constraints. So first, the additional capacity is at most equal to the remaining available capacity. And we also assume that the available capacity depends on what was previously booked. So this is because, according to one of the logistics service providers, only limited changes are allowed from the initial commitment. So if, for instance, they have 20 booked slots on the train, they might be able to get an additional 5 slots later on. But if they only have, say, 5 booked slots, then it won't be possible to suddenly double the number of slots. And the last constraint states that the number of cancelled slots must not exceed the number of previously booked slots. The third stage, which happens in the short term when complete demand information is available, is a bit different from the other 2 stages. So at this point, there are actually 2 different decisions that need to be made. So apart from capacity decisions, the routing is also done at this point. So the decision variables at this point are the number of booked slots per service, which is the same as the other 2 stages. Then the number of emergency capacity that will be booked. So if there isn't sufficient capacity available on the existing services anymore, we assume that there's an unlimited supply of trucks at a high cost. This is because the logistics service providers we consulted also said that even in the short term, it's almost always possible to find a truck if you're willing to pay for it. And the third type of decision variables are the containers per order assigned to each service. So this has to do with the routing of orders. Then as a constraint, we have that the booked capacity must be at most equal to the remaining available capacity. We also have time window constraints and the flow conservation constraints. Stochastic demand will be included in our model by considering different scenarios. So, for instance, like in this example, it is assumed that in the long term, or first stage, only the distribution of demand is known. Then in the medium term, part of the demand is known, and this actually gives us more information regarding what the final demand is going to be. We currently only have data on the total demand and not on the time at which orders arrive. So we haven't decided yet how the scenarios will be generated. This is something we still need to figure out. Because there are 3 different stages, we also need 2 different demand distributions. The first one that contains the total demand distribution would be used for the long term. Then for the medium term, we would need a different distribution from which the short-term scenarios are generated. There also needs to be a way to include the additional information obtained from the demand that we already know in the medium term to generate those short-term scenarios. So for example, let's say that in the medium term we observe a higher than average demand. This means that we would also expect a higher than average demand in the short term, so around this point. So the average of the second distribution would actually shift up. On top of this, to account for the reduced uncertainty, we could also lower the standard deviation of the second distribution. Now, the way we're going to model the relation between those two distributions is something that we still need to figure out. In the next steps of this research, we're going to determine how to model the demand. We're also going to develop a solution method to solve the problem, especially for larger instances. Then we would like to apply the model with company data, and we would also like to expand the model with additional sources of uncertainty, but to make sure that our results are actually useful for the companies themselves. So this was my presentation. Thank you for listening. And if you have any questions, I'd be happy to answer them.
Okay. Thank you, Thibaut. Do we have any questions from the public? Well, so I will start with one question. You also mentioned something at the end. So you identified several sources of uncertainty, right? On the travel times, on demand, on the actual capacity. So which one of those are you actually including in the model until now? All of them, or?
Right now it's only demand uncertainty. So that's one of the next steps. So once that we have figured out how to model the demand, we can try to get some initial results and then expand the model.
Okay, and if I understood well, so there in your model, yeah, it's mainly related to the capacity booking on trains. Does it support this intermodal transport network, or can you consider transshipment between different modes?
Could you repeat the question? So consider different modes, you meant?
Yeah, because until now it was only trains, and then I think trucks on the last stage, right?
Yeah, actually,
or it can be any mode in the link.
The model, it doesn't really matter what modes we're going to use. So if it's modeled the same way. So for instance, if you want to model it with, let's say, barges and trains together, then it's also possible. So the modeling is similar. It's simply modeled in the same way. So every service will have, say, a certain start time, end time, certain capacity, and that's it.
Okay, thank you. So now we have a question. Could you explain how did you find decision variables based on the collaboration with experts from industry?
The decision variables. So the decision variables are related to the amount of capacity that we're still going to book. So yeah, we actually consulted several logistics service providers, and they told us these are the decisions. These are the decisions we would like to know more about. So I don't know if I answered your question right. Maybe you could tell me if it was clear.
Okay, I guess it was. So if there are no more questions, I guess we can finish the session now. So Thanks again to everyone present that listened. And of course, if you have any other question or comment or want to have some discussion later, we are available. Yeah, you have our contacts here, and also we have an exhibition booth, so you can contact us there. So thanks a lot and have a nice day.